I've sent you the teamwork. Teamwork number 4. Okay. All right. Let's get to the second half of the game. This morning, Celtics beat the shit out of Sixers. Have you watched the game? What a charade. All right. Please come back 5 before 12. All right. Thank you. So let's get to our work. And well, this is the lecture 11. So as I said before the before halftime, most of you, I mean this course, because we only have 16 weeks in the semesters, and it's impossible for professors to ask students to develop a very complicated project on silicon. It's impossible. So most of the case in the past 30 years, as I say, I always ask a student to finish at least an 8-bit adder complexity or higher. That's all. And I never ask a student to develop something like this. It's called the sequential logic. Basically, this is a controller. Okay, everything you said about the control is based on the sequential logic. The control means that you are going to take two things into your considerations, then you make a decision. So the first thing is what happened now. What happened now? Okay, and the second thing you take into consideration to make a decision is what happened before. What happened before? What is the status now, and what happened now? For example, right now you take the course, and some of the students drop out already. All right, that's understandable, because the students make a decision like, okay, what happened now is that I cannot catch up with professors who wants course. That's one thing. And what happened before is that in other courses, okay, I might have a risk to fail others. So I find a way out of this shithole is that I'm going to quit this course, then to save others. Let's make a quick decision. It's understandable. Okay, just like you make a decision every day after you wake up. Okay, after you wake up every morning, the first thing crosses your mind, okay, what time is it? Okay, what is the state about, okay? What time is it means what the state I am, okay? Because if you wake up around like 7:30, so you make a decision quickly, oh, okay, 7:30, I still have 1.5 hours before the class begins. I can go to breakfast, okay? Maybe I can make some phone calls to wake up my girlfriends or boyfriends, so we can go to the class, go to school together. So that's how you make a decision. But for the adders or the multipliers, you don't do this kind of decision. You take whatever you have, then you make the arithmetic operations. You take two operands, you add them together, that's adder. You don't have to make a decision, okay? You take two operands to do the multiplication, that's multiplier. You don't have to make a decision, you just do the machine job, okay? The machine job, you don't think, you work, that's all. Okay, so sequential logic is something above the combinational circuits, okay? You have to make a decision. Then you have to watch two factors, as I said, what happened now and what is the status now, okay? So this is the, the core of this lecture. But however, all the meaningful systems, they are all sequential logic, okay? For example, the alarms, okay, the security systems, okay, the traffic light controllers, they are all sequential logic, okay? So combinational logic, output depends on current inputs. That's what happened now. I don't care what happened before, okay? I just like to have a party, okay? Because I won a jackpot, okay? I like to throw parties to celebrate. That's what happened now. And sequential logic is kind of different, okay? It's quite different from the combinational. The output depends on current inputs and previous inputs. That means the states, okay? Status right now, okay? So you got to remember what happened before. So requires separating previous and the current and the future. So it's about a decision. Decision means what I'm going to take, what kind of action I want to take, okay, in the future. So, and this is called the state or tokens. State is official names in this course. State means a status. Okay, state sometimes is referred to country. So the official name is called the state. So while Uncle Sam is called the United States of America, okay, because states for the country, okay, on official paper, okay. The state means the status, okay, in this course. Token is quite easy. Have you ever playing the claw machine? A lot of stores on the streets are claw machine, okay. They use coins. Okay, the coins sometimes refer as token. If you take the subway, for example, the Kaohsiung subway, okay, you pay. If you don't have the card, you go to the machine, you insert a bill, and then you ask for the token to be pop up from the machine. So use the token to pass through the gate. It's called a token. Okay, so these are two types of the sequential logic. The first one is the one that we are going to talk about today and Wednesday. It's called the finite state machine. Okay, finite means that the number of states is limited. Okay, then you might ask, is there a machine called the infinite state machine? My answer is yes, but it's not a cover in this course. Okay, it's not in this course. If we are talking about infinite state machine, then we are going to have a big trouble. We are going to run out of time. Okay, and the second one is called the pipeline. Pipeline is a term referred to that everybody sitting on its own station, okay, and doing the repeated regular work all the time. Okay, it's called the pipeline. Okay, now we are going to introduce these two types. Basically, our attention will be focused on the FSM. Okay, sequencing. What does it mean, the sequencing? Sequencing does everybody is standing in a line, walking toward the end of the road, okay, one by one. Okay, nobody going to surpass the others. Okay, that's called the sequencing. So if the tokens move through the pipeline at a constant speed, okay, or no sequencing elements would be necessary. So that means, okay, on the highway, picture this, okay, if we assume that every driver, okay, fix the speed of their car on a constant speed, like 55 miles per hour, okay, constant speed. Okay, that means no one is going to use a brake because everybody, okay, is moving forward on a constant speed. That why do we need the brake? Okay, but unfortunately, it's impossible because we always have a driver who are slower drivers, okay, like old ladies, okay, old guys like me, we like to be safe. We drive slowly, and okay, there are other drivers who drive a very fancy sports car, the Porsche, the Lamborghini, maybe Ferrari. Okay, they like to demonstrate the capability of their car performance. So they like to drive very fast. So it's impossible to have a constant speed on the highway like that. Okay, the only thing in this world that is a constant is based on the speed of light. Because the speed of light is a limitation of speed in the universe, so it got to be a constant. So the only thing that you can find in human civilization is a fiber optical cable. Because every packet is traveling with a light of speed, so it's a constant. That's it, it's a constant. So you don't need any buffer, any checkpoints, any token, or any station to synchronize the speed of every packet they want to do the travel. So light pulses, tokens, are sent down the cable. Next pulse sent before the first reaches the end of the cable. So no need for hardware to separate the pulses because everybody moves forward in a constant speed. So why the hell we need a station to check the speed? Because we already know that everyone, okay, using this cable will travel with a constant speed. Then it's cool. Then it's cool. Okay, the only thing difference between this cable and that one is the time gap between two pulses. It's called the dispersion. It's a dispersion, okay, between the pulses. That's all. And this kind of design is so perfect. Okay, only, as I say, this is the only thing I can think of, okay, without the consideration of any checkpoint or the buffer station, that's this kind of thing. It's called the wave pipelining. As I said, because the light of speed, okay, is the highest speed in this universe. It's constant. Okay, it's written by Albert Einstein, and it's verified by a lot of physicians, okay, already. Okay, so in most of the circuits, it's impossible to be done. So the dispersion is high. So the only thing that we can do, okay, to maintain the sequencing without the bad things happen, like, okay, the later token is going to pass or catch up with the previous token, is that we have to delay them. Delay those the fast guys so that they don't catch slow ones. So that's why we need a police officer, highway patrol, okay, on the highway to watch, okay, those young men driving the Lamborghini, make sure that they are not going to hit anybody else. Okay, that's why. So we call that, it's called a delay. We have to slow them down to prevent, okay, bad things happen, to prevent the collision, to prevent somebody get killed. Okay, that's called the dispersion. Most of the circuits, dispersion is very high because some of the tokens will be fast, some of the tokens will be slow. Okay, you gotta have a mechanism to make sure everybody still standing in line one by one and without any passing, suppressing, these kind of things happen. Okay, this is called the sequencing. Okay, so sequencing, that means that we gotta have some extra mechanism. Extra mechanism means that we gotta have extra overhead. Okay, we gotta hire, okay, many capable men who are called the police, who are called the highway patrols, okay, to check the status of the highway all the time. It's called the overhead. And here in our circuits, we use something that you already learned. It's called the flip-flops. Flip-flops is going to delay the token, faster token, so that they are not going to catch up with others so that the sequencing is messed up. Okay, so this is called the, I call this kind of thing, it's called the buffers or the stations. So the fast guys will be slowed down and ask them to take a break over there, wait for others, okay? So of course, these flip-flops will add delay. Of course. Okay, this is a price to pay. You are not going to break the sequencing, now you gotta pay something to make that happen. So the circuit will slower than just a logic delay. So as we mentioned that combinational circuits has its own intrinsic delay, then if you want to create if you want to design the controller or the sequential logic, you got to pay the extra price, okay, for this one, okay? This is called the flip-flop delay. And it is AKA referring as the sequencing overhead. Some people call this clocking overhead because it's driven by clocks. Okay? And there is another type called the asynchronous logic. We're going to get to that part later. So the bottom line is we are going to have sacrifice, side effects, okay, in order to keep the sequencing. Make sure everybody stayed in the line, okay, move forward effectively. Okay, this is called a sequencing overhead. So here we go. So then, these are the contents of this talk. We are going to go over what the memory elements is, okay, that are delay buffers, okay. First thing first is that bistable devices, then memory elements, okay, and then dynamic memory elements. And then number 4 is timing issues. Timing is what the students hate most, okay, because you are going to deal with timing. And well, recently I found out that students are short of the capability to do the mathematical derivations. Well, I don't blame you because it's a problem of the generations. Well, I'm not sure whether I talked about this before. Well, about 30 years ago, 40 years ago, we did not have internet. We don't have cellular phone. Okay, we make real friends. Okay, we use the landline to call our friends, get out their houses and play basketball in a stadium or in an outdoor course. Okay, and we call our friends to get out, to get in the middle of the night, to go out and have some late meals together. Okay, and we don't have Food Panda. We don't have Uber Eats. 30 or 40 years ago, we have. If we want to get to it, we have to find the door steps and get out. All right, and timing issues, and another thing is that we did not have too many fancy software tools. We did not have strong computers to help us to do the analysis. So we have to come down to our pen and pencils and the papers to do the derivations. So this is the problem with generations, not you. Okay, and the last one is the pipeline system. We are going to go over it very quickly because none of us were going to realize any system in the pipelining. Okay, so let me introduce the devices first. Okay, type of sequential circuits and bistable, and what happened to these the devices. Okay, they might create some problems. Okay, before we go to the details, so let me introduce what the finite state machine is. Okay, finite state machine, you can consider that it is my assumption that you should be able to know this. You should understand what finite state machine is. Okay, basically I borrow this figure over here. So you have a combinational circuits. Okay, combinational circuits. Combinational circuits takes whatever happened now. This is called the input now. Of course, it generated output. But not only, if this is a pure adder, it's no problem. Okay, I take the addends, operands, and I do the math. Then I deliver the sum and the carry. That's all. Okay, so this is how it works. But the difference is this one. Okay, we are going to have an array or a pile of memory elements. Okay, and they are going to remember what happened before. So this is the second box. For the pure design, pure logic design, it's all about the combinational circuits. But if you want to remember what happened before, you got to have a mechanism. Okay, some memory elements to remember what the state is. So this is where the state is. Okay, and it can be flip-flops. It can be latches. Okay, it can be memories. Anyway, you got to have something to remember what happened before. Okay, flip-flop is a major mechanism we use. Okay, latches is number 2, and memory is one that if your system is too complicated, you got to use a memory because we can use the DRAM, SRAM to do that. Okay, I'll give you an example to show what the difference is. Okay. So if you are adder, okay, this is a adder, ripple carry adders. So you have A0, B0, and you have a C in. Okay, then you do your full adder addition. Right now you're an expert already, so you are going to have a sum 0, right? And you gotta then you generate the carry out, right? Carry out. So this is C1, and this is A1, B1, and you use a full adder again. Then, of course, you're going to have S1. Then this way. Okay, all the way down. Okay, so you are going to compute and, okay, something like this. Okay? You don't have to remember what happened before. You simply take two operands and do the addition, that's all. Okay, this is called the adder. Okay, it is just too simple that we cannot take this as a final project. But let's use this name. Okay, if this is an adder, we use a symbol view. Okay, we have a 4-bit RCA. This is a symbol over here. So this symbol over here is that we have two operands. We are going to have a sum and carry on. Now, what is the difference between this one and the other one is called the counter. Okay, the counter or the accumulator. I guess the accumulator. Okay, counter. Counter or accumulator. Okay, then what happened right now is an adder. This is the adder, right? This is the adder. So what if we have an adder? This is an adder, or it's RCA, and never mind. RCA, just like the one before. So we got dump the count. Okay, now this is one exactly the same as over here, right? But we got to remember what the count is right now. And then I add another one into it. Okay, and this one is a states. For example, if we have a counter, after the first counting, okay, we count from all zeros to 0001, is that right? Okay. Then in the second addition, we got to remember the 001 and add another count, which is 1 as well. They will become 00010. Okay, and we keep it counting up as a counter or accumulator. So the adder is a combinational logic, but either the counter or the accumulator, they are finite state machine. Because the next count depends on the count and what happened to the previous count. Okay, that's the definition. These are very good examples for you to understand what is the difference between a combinational circuits and a sequential logic. So this is the graph shows demonstrated in the textbook. See that we have a combinational circuit over there, and remember next stage, and the flip-flops are used to remember what happened before. So finite state machine is defined by 5 variables, I, O, S, delta, and the lambda. Okay, we have a state transition. State transition is the is operand between I and S. And the function is delta. Okay, I as an input, and S we have mutual functions, and the function is defined by delta, and it's going to the next stage. And the output functions, we have 2 definitions. Okay, if the output function depends on input and the state, we call it a mini machine. And another type of finite state machine is called the Moore machine. Moore machine is that the output depends on the state only. So right now you understand the difference between the counter and the adder. Right now, I'm going to show you what the difference between the mini machine and the Moore machine. I'm going to erase all of this. Okay, the output here depends on the input and the state. So this figure shows it is that it's a mini machine. Okay, this is definitely a mini machine, all right? And what is the Moore machine? Moore machine is slightly different. Moore machine is that we still have a combinational circuits, and then we are going to have a state over here. And this is the output. This is the output, okay? This is the output. So out the stage. Then it's coming back. Okay? This is the inputs. This is what the state is. This is the output over here. So the states, this is the states. Okay? So we move this red box from here to here. Okay? And what is the difference of these two? Because here, outputs depends on what the state is. It's nothing to do with the input over here. And then the next question is, okay, you are going to ask is which one is better? Okay? I'll tell you what, okay? Most of the textbook, they like to use this way. Because it's easier for students to understand that how sequential logic is, okay? But for those guys in the industry, they prefer this type. Because that one is easy to derive, and this one is slightly complicated, but it's better in terms of something. What is that? It's pretty easy, okay? This is Moore machine. I'll tell you what's going to happen. Remember, I keep emphasizing one thing, okay? This world is not perfect. We always have bad guys in society, okay? We always have certain people, some people, they don't follow the rules. And in the circuits, we always what? We always have noise. We always have noise, okay? So the noise, if it's a couple, over here, this is noise. If we use the mini machine, the noise will be directly injected, or it is a couple to the output. So the noise is transparent from the left to the right. Okay? But here, remember that the state is driven by what? By clock. Unless the clock is activated, otherwise any noise will be stopped right here. The noise is opaque. It's not going to pass through to the output. So in terms of the noise rejection, this one is much better. So that's why I told you that in reality, most of the industrial guys, they prefer this type because it's noise insensitive. The other one is noise sensitive. Okay, what? Because we have a states flip-flops over here, and it's controlled or driven by clocks, unless the clock is activated. And if this is edge trigger, you only have a limited window for the noise to go through. Okay, you have a very limited window. This is edge trigger flip-flops. And edge trigger means that only the rising edge or the falling edge and the time of these edges are very limited. So the window for the noises to become a problem is very limited. So it's noise insensitive. Okay, this is the basic definition of two types of machines. Okay, mini and Moore. Okay, so these are the two types. Okay, the top one is is Moore machine, and the second one is mini machine. See that? The inputs directly go to the combination over here. These two figures mean that there are extra combinational circuits besides the computation one, okay, over here. Okay, this one is mini machine, and that one, see that? The inputs will be stopped the noise in the coupled in the input will be stopped by by the flip-flops over there. So there are two types. The upper one is the born machine. The second one is mini machine. So it's pretty straightforward. Okay. Of course, we need memory devices for us to remember the status. So because we like to have memory elements, so memory must be a device to remember one of the two states. So it is called bistable devices. Okay, bistable devices. So bistable device is even stage, not gates. Even stage. For example, even stage, we have 2 or 4, okay, or 8 or 6. Never mind, as long as it's even numbers. So 1 over here, we're going to have a 0 here in the middle, in between, and 1 at the output. So it's circling back, it's locked. So the state is locked. Okay, it will be stabilized as long as the power is on. So when we have an even stage of inverters, it definitely will be bistable devices. Okay. Then if we have an odd number of stages, then we are going to have an oscillator. Because the 1 over here, it becomes 0, and it's circling back to change it to 0 and 1 and keep looping that way. Okay, so it becomes an oscillator. So this is for the buffer or the flip-flops or memory devices. And this kind of design, odd numbers, is definitely for the oscillator. It is for the usage or application of clock generator. Okay, clock generator. All right? It's over here. So this is bistable state devices. Okay? But the thing is, we got to consider some terrible fact that even though that we have bistable devices, we have a risk that it might run into the state that we don't like. Okay? Bistable devices means that this is one that we like to use. Okay? Theoretically, we have a 1, 0, 1. It's perfect. Now, the best things might happen is that, what if we have a noise or the unstable power supply? Then we are going to have a voltage here, okay? It's not in the VDD or not in the ground, it's somewhere in the middle. Just like we drop the ball. We drop the ball, this is a hill. From the sky, okay? And then because of noise or other coupling effect, it might go this way or go this way. Okay? So it's called the meta-stability. So if that ball sitting on the top of a hill, it's called a meta-stable. Meta-stable means that it might go to the left, it might go to the right. Okay, it's called a meta-stable. And that's a risk to have an error. Okay, that's a risk to have an error. So if we want, excuse me, if we turn the behavior into figure, then we understand what is that. This is the possibility. Okay, if we ignore this one, look at this blue line. It is a very typical inverter function. So when the input is high, then we are going to have output is low. When the input is low, we are going to have output high. It's perfect. And this is the transfer function of the other flip-flop is this way. Okay, so what is a stable state? Close to these two terminals is a stable state. What is meta-stable? It's somewhere in the middle. You don't know which way it goes. Okay, you are confused. You are sitting in the cross of two streets. You are confused. You don't know which direction you should go to have a better life. Okay, something like that. It's a meta-stable. And this figure, as a nickname, it is called a butterfly figure. Okay, that figure over there is called a butterfly. If you hear this name, now you understand what it's talking about. Butterfly diagram. Butterfly, the beautiful insect Okay, you will see it in the Chaisa Mountain area. It's, butterfly, sorry. Butterfly. Very pretty creature. Butterfly. Sorry, my English is so bad, I cannot spell it right. Just like the George Bush. Butterfly. Diagram. Very pretty creature. Okay, well, too bad. Our environment protection is so bad that a lot of butterflies are gone forever from this island. It's too bad. Feel sorry for them and feel sorry for our human beings. Well, economy is one thing. Everybody likes to have a lot of money in the pockets, so we sacrifice a lot, including the environment. And the damage might not be reversible, okay? The damage might not be recoverable. Well, I think you heard a lot of this kind of story in the newspapers, but we are only human. We struggle between two things, okay? To have a better life, okay, or to have a better environment, okay? But most of us select that we like to have more money in the pocket. That means a better life. Okay, I'm not sure this is correct, okay? But we cannot forecast, we cannot see what happened 100 years later. Okay, we only care about 10 days later, that's all. It's too bad. Okay, for example, the interesting thing that you just take the teaching evaluation questionnaire to judge whether my teaching quality meets the standards of the university or not. It is kind of a thing. It is my belief. Everybody get paid needs to be evaluated. Everybody get paid must be evaluated. Remember, one day you will go to an organization, a company, or a school, or a graduate school, something like that. Most of you will go to a graduate school. And then, in the end, you're going to get a job in the industry, okay, or in a school. After you become a PhD, you want to find a job. Remember, I'll mark this down, okay? Everyone gets paid shall be evaluated, okay? No exception, no exception. Why is that? Because this is a way to check the quality of your service or your job. Is a job. And it means even more. It means a lot for those young faculties, young professors, because they have maybe another 10, maybe 20 years of career ahead. Okay, they have the responsibility to educate the young generations to come. So we got to do that. Okay, but it's kind of not that useful for an old guy like me, because I only have like maybe 3 or 4 years left in my career. But unfortunately, I have to put this way: a lot of young faculties in the university, not just in our school, they don't pay too much attention to their teaching. Okay, it's kind of sad. Okay, I don't have too much time to talk about that part. But this is not their fault, basically, because all the young professors, you're going to work, some of you, you're going to work with them. They care about one thing and one thing only, that is a promotion. And the promotion means that they want to be elevated from the assistant professor to associate professor, and then from the associate professor to the full professor. It's called a promotion. Promotion means a lot. It means not just the increase of income. It also means the increase of their visibility. But the thing is, the weighting, okay, of the evaluation system of this promotion does not put too much in teaching. The entire evaluation system of promotion very, very focused on the publication. So this kind of a weird thing, kind of distorted the judging system, okay, encourage young faculties to spend a lot of efforts and time in publishing papers, okay, and they don't want to waste too much of their energies in teaching, or at least to improve the quality of their teachings. So this is one of the reasons why there are only a few professors can provide English courses in this department. Okay, I'm not sure, I'm not saying I'm the best, but at least I can give lectures as long as I like. Okay, I don't prepare any draft. Okay, I never pause for anything. And you gotta make sure, polish yourself for this kind of thing. And for those young professors, well, sometimes I feel pitiful for them. Okay, they have to struggle. They're just like beginners. Okay, but the thing is, they are strong in the ocean, and they have to find a way to swim, to find a dry land to stay alive. And publication, the evaluations of because we put too much scores, weightings on the publications, so that these young faculties, they like to publish a lot of papers. Okay, I'm not saying papers is no good. Papers are fine. But if you keep emphasizing the publications, that will create something very distorted. Which is that? Which is what? Okay, that means they have to, they have to fight for a lot of grants and waste a lot of times. And 99% of papers are junks. 99%, okay, are junks, because 99% of the series or reports published in the papers will never be used in real life. Okay, that's my observation. That's fine. Okay, but this is a rule of the game. We just follow the rules and play the game. That's all. Anyway, I just let you know. Okay, so sorry, waste too much time to talk about this kind of bullshit. All right. So what is the problem of the metastable? And this is an example to show you what's going to happen. Okay. Now, right now we have two stages over here. The first one is called a synchronizer. Okay, we have an input coming from nowhere. It's a synchronous input, because we cannot predict when the X will be effective, will be activated. All right? Then, after the D latch, we have a W. Theoretically speaking, W shall be exactly the X. Okay, if the D flip-flop is the DFF1 is activated. Then we have an X over here. We have a clock to driven the second stage. The second stage is driven by a clock as well. And this is synchronous input, Y and Z. Technically speaking, because the input of these two D flip-flop, they are from the same W, the same input. Theoretically speaking, Y and Z shall be the same, right? Technically speaking, if you don't look at the detail of the timing diagram, you say, okay, Y must be the same as Z as soon as the clock is effective. So this is what happened, okay? This is the time to the end. So the clock is here, and we have a period, a T clock. So when the clock is high, then X is a sample. X is a sample. And X, unfortunately, is a very short period. Short period is just a very narrow pulse. So it's over here. Then the first stage, take a sample, and it's not high enough because the time here is very short. It's very limited. So as you can see, it's not a poor to very high like a VDD. Then, because of the leakage, they keep dropping. It keeps dropping. Okay, now funny thing happened. Then we have a clock over there. Okay, in the second rising edge, okay, Y and Z, two flip are going to sample the W over here. Okay, then you're going to find out one thing very interesting. One of them could be 1, the other one could be 0. Because here, the voltage of W keep dropping to the middle of nowhere. Okay, it's somewhere between 1 and 0. And the interpretation of two flip-flops might be different. Because the process variation is there. Okay, you cannot get rid of it. So the Y and Z, they might see different phenomena. They might see different outputs. So this is a hazard of metastable states. I'd say it's unthinkable, right? Because if you don't look at the timing behavior, you just look at this figure, the circuit diagram, you say, of course, y equal to z. Okay, end of discussion. It's distributable. But if you look at the timing behavior, it's not. Okay, as I said, the world is not perfect. Okay, of course, some serious guys, they do mathematical analysis to find out what the problem is. This is an interesting phenomenon. Okay, you don't have to remember this. I cannot. It is called the MTBF, mean time between failures. Okay, that means, okay, two failures. What is the time between two failures? Okay, let's run the simulation over time. Okay, let's assume we have unlimited resources of computers, okay, and the storage. We can run it, and we'll find out this interesting thing. Okay, the overall time, okay, assume it's a T clock, must be larger or at least equal to the recover time plus the delay plus the setup of the D flip-flop. Then this is an equation developed by a very wise guy. I don't know how he come up with the equation. Never mind. We just engineers. We take advantage of all the equations that have been reported. So we run the random mass. So the mean time between failures. So how long between two failures? Okay, can be defined by this equation over there. So this F is the operating frequency. A equals to the number of asynchronous inputs changes per second. That means how many times X changes. Okay, T0 and the tau, okay, are synchronized constants. Okay, this is the period, and this is a time constant. Okay, so plug in the numbers, we see very interesting results. As I say, you don't have to remember that. Okay, now let's assume the clock is 10 megahertz. And the A stands for what is the frequency X changes, okay, the input changes. And 7474, this is a typical D flip-flops that you can purchase in Changming Street, okay, over there. So 7474, the mean time between failure, if it's 20 nanoseconds and 40 nanoseconds, you're going to find out that, okay, for 20 nanoseconds, 5.66, 10 to the fourth seconds will happen 1 times, okay? And then if the number changes to 40 nanoseconds, okay, that means it could happen in this period of time. It's become very meaningful, okay? This is very short period of time. You can ignore that, but this is a number which is visible to human being. Okay, that means during this time, okay, we might have this phenomenon, or might have this phenomenon. Okay, this is tell you that the failure could happen anytime. Okay, if you don't design the system well, then something could happen to you and your design. Okay, now if you change to 100K, okay, that means the number, the clock is changed to 20 megahertz and 40 megahertz. That means the last one give you this number. Okay, every 400 years, you are going to run into this kind of error once. Okay, so this is just the estimation of the numbers. Okay, this is another example. Don't worry about it. Okay, so how do we get rid of it? Because from time to time, okay, even though that the MTBF equation told us, or already tells us that the failure could happen in that kind of period of time, but it's still a problem. So how do we attack metastable states? We don't want this to happen, Okay, even though every 400 years it happened once, we still don't like it. Okay, we like to have our machine can run permanently, okay, as long as the power is on. So we need something to help us. It is called a synchronizer. Synchronizer is that, okay, this is what I tell my students, but a lot of students, they never listen to me, even they are graduate students. The asynchronous input, okay, must be buffered by D flip-flops and then used as real signal to be processed. Okay, you can use this way or this way, that's fine. The only difference is this one depends on how many counts. How many counts? Because this is every clock it buffers. And this one is, we got 2 clocks, 2 clock cycles, 4 clock cycles, we buffer it. Either way is acceptable. Okay, let me tell you why this is important. Okay, I'm gonna erase this, okay? So you understand why this is important. Okay, you are going to do your final chip design, right? And this tells you how to prevent failure at the step number 1. Okay? So this is your design. Assume this is a COA. I know somebody use it. I know somebody select this idea. COA. Okay? So the students who select this topic is going to, okay, design the COA based on the design in the textbook, then use the pad frame okay, pad frame, and you have a 40-pin pad, 40-pin count, 40 pads frame. And students, because we are beginners, the only thing that we can think of is 8-bit. So this is a COA. So let's do the count. Let's count how many pads you have. 8-bit inputs, right? 8-bit inputs, that's A and B. Then we are going to have a sum, 8-bit and the carry out equal to 1. Is that right? Basically, right? So let's count the number. Just for the signal part, a total number is 25. Okay, but limitation is defined by the TSR. You only have 40 pins. Okay, you got to be aware of that. So this is just fine. Okay, seems no problem. And on both sides, you got to have a VDD and the power. So VDD and the ground. Okay, we got to have 2. Then 4 sides, we got to have 4. That's 8. Right? So right now, we have 25 signal pins. Okay, 8 for power and ground. Okay, we are going to use every number, every pad. Then what else we need? We need a reset. Right? We need a clock. Is that right? Okay, we need a clock. So the reset one is the one. And because this is a digital design, you got to have a test mode or a normal mode. It's 1 pin. So this is basically you need to carry out this design. 25, this is 11, is 36, then you are safe. So for those students who select COA or Manchester adders, okay, you can directly use parallel input and parallel output, no problem at all. But for those students who select multiplier, if this is a multiplier, then you have a big problem. What is that? Because this is a multiplier, right? So what you're going to have? You are going to have a product, which is 16-bit. 8 times 8 equals to 16 bits, right? So if you want to keep doing this kind of design, so you're going to run out all the pins. If right now here, this is 32. 8, 1, 1, 1. So that's 43. Then you are screwed. You run out of paths. So the first one who select the COA is very smart. It's easier. Okay, let's assume you select the COA. Okay, you're a lucky guy. You pick up the good one. Okay, that saves you a lot of trouble at the king count. Now let's go back to COA. So no matter this is a COA or not, right now you're going to do the addition. So the signal, let's assume, comes over here. Sorry. Usually the students like to do this way. This is 8, comes over here. This is B, 8 bits B, coming over here. Goes through over here, and they are coming over here to be added. Just like what the textbook says. 8 bits of A, 8 bits of B coming together into the addition part. Now remember this one. You cannot guarantee all the paths, all the paths, the length of all the paths from A and B, they are equal. It's impossible. No way you can do that. That means the signals from over here, they will arrive the core, not in the same time. Right? They will not. So you got to use this kind of thing to synchronize it before you take the action of addition. So I'm telling you that before the COA, you got to do some adjustment. Okay, this is your COA over here. And then you got to have register, flip-flops, register. This is for A, and this is for B. Then the B coming over here, and the A coming over here. Then they will be synchronized to go into the COA. Okay, so the register D flip-flops, okay, are required to synchronize the signal going to the core of your design. Just like the one over there, that's synchronized because the A and the B, they are asynchronous inputs. You cannot guarantee they arrive simultaneously to the adder. That's impossible. And then don't forget on the other side, after you do this is output register. After you do the calculation, right? You cannot ensure the sum 0, sum 1, sum 7, and the carryout will be delivered to the outside simultaneously. It's impossible. So you got to have a mechanism over here. This is also register, flip-flops. And this one is going to synchronize the output together, okay, and give to drive the paths simultaneously. So no matter it's the input or output, any design needs flip-flops, register to synchronize it. Is that clear? Okay, it's better for you to do that. That will guarantee the success of your measurement. Otherwise, let me tell you what, okay, how do you generate these inputs? You use the function generator. Function generator, they are not guaranteed to synchronize everything. It's impossible. You cannot assume that the machine is perfect. It's not. It cannot be that way. It's impossible. All right. So this is a way to do it. And what is about the test mode? Test mode means that you have some internal data, which already over there. For example, you use a very stupid idea. You use an extra pin. Okay. Let me erase this one. Okay, if the chip is entered to the test mode, okay, you can use a serial pin to input the data, 8 bits, 16 bits. Whatever you like, because you already know it. And they are going to send it a bit by bit into the register. Of course, in the test mode, this got to be disabled. All the data comes from here, single input. After 16 bits, 16 cycles, then you write these two register. Because you already know the answer over here, the original data, you can expect output. So this is called the test mode. Test mode means that you can send in special pattern, which you know the answer already, and you just monitor the output, whether it matches what you expect or not. So this is for the test mode. And reset is an initialization to flush everything here. Otherwise, the D flip-flop could be stored with an unknown. So the reset is used to, at the beginning, after the power is on, you are given all zeros or all ones, that's fine. That's all. Okay, so you got to think clearly, okay, how to fully use the prep frame, the pin count that you are allowed to use, okay, and make sure that your design, okay, has a very high chance to be successful. Okay, this is the method to attack the metastable. This one that you should consider to use them in your design. Okay, latch and flip-flops, memory elements. We have 3 types: latch, flip-flops, registers. Okay, and register is a given number of flip-flops, and one flip-flop is 1 bit register. That's the basic definition. So latch, okay. So latch is a level-sensitive device. So the difference between the latch and the flip-flop is that whenever you see a triangle, that means it is edge trigger. It is a flip-flop. If you don't see any triangle, that means it is a level-sensitive. Okay, when it's high, it's pass, and it's low, it's not. So these are 2 examples. Okay, this is a clock. And this is a data pin. All right, this is the behavior of a latch. This is the behavior of flip-flops. Okay, then let's go to see the full timing diagram for you to understand. Okay, this is how it works. Okay, I love my coffee. Come on. Before the session is closed, I got to tell you this. Okay, over this weekend, 1, 2, 3, 4. 4 of my lab students and assistants, they got they got positive about COVID-19. It's where it's coming back. Okay, 4 out of 30 members of my lab sent me emails over this weekend that they use the quick detection strip to find out they are positive. COVID-19 positive. I don't know what the hell is happening. But the WHO already announced that the COVID-19 is no longer a pandemic problem, but it's just become a flu. It just become a heavy flu. So just take care of yourself and don't do anything stupid, but the flu is still around. The flu is everywhere, every day, okay? It's where, so over the weekend, suddenly 4 members sent me emails that they got infected. Jesus Christ. Okay, let's go back to this one before it is too late. So if this is a latch, check this out. So this is clock, right? So if this is the latch, then when clock is high, all the data will be coupled, duplicated to Q, okay, with a delay. So the D, whatever happened D over here, will be copied to the latch. And the blue curve with an arrowhead means the sequence. This one is mapped over here, this one is mapped over here. So the entire waveform is copied. And then when the clock drops low, okay, and that means the latch is blocked. So even though that we have some variation over the D line, nothing will happen because it's blackout. It's blackout. And if you look at the behavior of the flip-flops, okay, flip-flop only takes actions at the edges, okay, either the rising edge or the falling edge. So in this case, there is no circle, this is rising edge. So it's all happened here. This is the rising edge, right? So we do the sampling over here. See, and there's nothing, this is ground. So the flip-flop stay slow. Okay, and then nothing happened until the next rising edge. And here we do the sampling again. We find out that D is high. Then we put it high. Okay, and this blue curves with arrowheads stands for the sequencing. Stands for the sequencing. Okay, so this is the this is the behavior of latch and the flip-flops. Okay, and we have more figures to show you. So the top one is the top one is a latch. The second one is the D flip-flop. So this is the gate over here. This is the setup time, and this is the definition over here. Setup time and the hold time. Okay, and then this is high. So when this is high, we are going to copy everything down. It's transparent. It's transparent. Okay, this is the latches over there. Okay, so how do we avoid the transparent property? So there are several types. In order to prevent that kind of transparent, of course we got to use a flip-flop, master-slave flip-flop, edge trigger flip-flop. Basically they are the same, but different this design strategy. The last one is a pulse latch. Pulse latch is the one that widely used in industry, not in the academia, because pulse switch is a circuit, depends on the sophistication of how well you design the circuit. The tiers are here. So before I close the session, I'm going to ask you to do your teamwork, okay, based on the schedule that we have. Excuse me. Okay, this is a teamwork number 4. So let me assume that you follow my instructions, okay? So the first, in the beginning of the stage is that you prepare the proposal to the TSRI. Then you spend 2 weeks to draw the pre-layout simulations. Right now it's a time for you to do the layout simulations. So in the coming week, let me assume that you already finished some of your pre-layout simulation, circuit simulation. Then it's time for you to do some layout. Okay, and the layout is that I'm not going to ask you to do the full layout of your entire chips. At least you should finish at least a part, a few sub-blocks design. For example, if you're doing the COA, at least you should finish. You should be able to finish the one single bit full adder design and go through the verification, online and offline post-layout simulations. Then you got to update your progress report, okay, to address the size and online verification of your design. This is what I ask you to do in the next 2 weeks, because we are going to have Wednesday makeup course, and this part shall be, we expect you to hand it in 2 weeks from now, which will be May 29th. Okay, that's all. If you have any questions, I will encourage you to contact those beloved TAs over there. Okay, they will help you. And after the May 29th, okay, that's my last lecture. In the next week, 6 June, June 5th. Okay, you two boys got to give a lecture to talk about how to prepare the final submission of the tape-out application, and then explain how to do the midterm exam problems. Okay? Midterms, yes, how to do that. Because I might use some of the problems again in the final. I might, okay? I might. All right, then if there is no problem, we close the session over here, and I'll see you in Wednesday evening. Okay?